welcome to the deep dive. This is where we dig into just stacks of information, really sift through it, and pull out the really fascinating stuff for you. And today, wow, we're going on a journey, one that, well, humanity's been dreaming about for ages, right? The idea of other worlds out there.
Oh, absolutely. It's ancient, isn't it? Goes way back. I mean, think about Democritus, the Greek philosopher, thousands of years ago.
Right.
And he's there speculating about, innumerable worlds, other Earths,
Yeah.
basically, orbiting other suns.
Yeah. And for ages, that was, well, it was pretty out there, even dangerous to suggest sometimes.
Definitely dangerous. You just had to think about Giordano Bruno, right, in the
Mhm.
16th century. His fate was pretty grim for suggesting things like that. Heretical, they called it.
A stark reminder, yeah. Shows how far we've come.
It really does. But it wasn't just ancient philosophy.
No, exactly. Fast forward, you get Edwin Hubble, early 20th century.
Right. Hubble, the astronomer. And he had this, scientific intuition.
Yeah, he looks up, sees the stars are suns, basically thinks, well, our sun has planets, so
So why wouldn't other stars have planets, too? It seems so logical now, doesn't it?
almost obvious, but back then, that leap was huge, laid the groundwork.
And now, that intuition, that logic, it's exploded into this incredible reality.
Mm-hmm.
We are truly living in a golden age of, well, exoplanet discovery.
It's staggering. What's the number now? Over 5,600.
Over 5,600 confirmed exoplanets as of, August 2024. And that number, it's climbing so fast you can barely keep track.
It's incredible. And these aren't just dots anymore, they're real worlds.
Real worlds, and so diverse. We're finding things, types of planets, that just blow our old solar system-based ideas out of the water. Things we never imagined.
Which brings us to today's focus, because among this huge growing list, there's one planet that's really grabbed the spotlight, scientifically and, in the public eye too.
Ah, yes, a world of, intrigue.
Yeah.
And definitely some contradictions, as we'll get into.
We're talking about K2-18b.
K2-18b. It got famous pretty quickly, didn't it? That label. Potentially habitable exoplanet.
Exactly. And then big news, finding water vapor. Huge excitement.
Understandably so.
Mm.
Water's key, right? But then, more recently, even more buzz, these hints of potential biosignatures. Very debated, very cautious hints, but still.
Right. And that's where it gets easy to, get swept up in the headlines.
Absolutely, which is why we're doing this deep dive.
Okay, so that's our mission today. We're going to cut through the hype surrounding K2-18b. We'll unpack the discoveries layer by layer, the excitement, yes, but also the crucial scientific skepticism.
We need to look at how we even find these planets, how we study their atmospheres. What did we actually find in K2-18b's atmosphere?
And explore these competing ideas about what the planet is actually like. Because, spoiler alert, some of the latest science really challenges that simple habitable label.
Oh, definitely. It's a fascinating case study in how science progresses, how complex this search for life really is. It shows how every new observation can shift our whole perspective.
All right, let's dive in. K2-18b's debut. Where did it all start? This wasn't found yesterday.
No, not at all. It's been on the books for a while now. The initial detection was back in 2015.
2015, okay.
Yeah, during the K2 mission. That was campaign 1 of K2?
Now, K2, that was part of Kepler, right? The Kepler Space Telescope.
Exactly. Kepler launched back in 2009. Amazing mission designed specifically to find exoplanets using the transit method, just staring at one patch of sky.
Right, looking for those little dips in starlight.
Precisely. But then it had a mechanical issue, lost some of its pointing stability, but very cleverly they repurposed it into the K2 mission.
Ah, so K2 is like Kepler's second act.
Sort of, yeah. It observed different fields of view along the ecliptic plane, and K2-18b was one of the really significant finds from that K2 phase.
Okay, so found in 2015 by K2. Where is it? What's its cosmic neighborhood like?
It orbits an M-dwarf star, one of those smaller, cooler, redder stars compared to our sun.
M-dwarf, okay.
This specific one is called K2-18. It's an M2.8 type, technically, and it's about 124 light years away from us.
124 light years. So, astronomically speaking, relatively close. Close enough to study in detail anyway.
Exactly. It's in our galactic neighborhood, you could say. It's
Yeah.
located in the constellation Leo.
Leo the Lion, okay. And the star system itself, K2-18, how old is it? Does that matter?
It matters quite a bit, actually. We think the system is pretty old.
Yeah.
There's a technique called gyrochronology.
Gyro what now?
Gyrochronology. It basically estimates a star's age based on how fast it's spinning. Older stars tend to spin down over time.
Huh, okay.
And based on that, K2-18 seems to be around 2.4 billion years old, give or take maybe 500 million years.
So 2.5 billion years old, roughly. That's quite a long time.
It is plenty of time for things to happen, potentially. For planetary evolution and, well, if conditions were right, maybe for life to get started and evolve.
All right, so we've got its location, its age. What about the planet itself, K2-18b? What are its vital stats? Size, mass? Is it like Earth?
Definitely not an Earth twin in size. Its radius is about 2.6 times Earth's radius. So more than 2.5 times wider than our planet.
Okay, significantly bigger, like stacking 2.5 Earths.
Something like that, yeah. And its mass is even more substantial. It's estimated at around 8.6 times the mass of Earth.
Whoa. Okay, so much heavier too. Not a gas giant like Jupiter, but way heftier than Earth.
Exactly. That combination of size and mass immediately tells us it's something different, something we don't have right here in our solar system.
And its orbit. You mentioned it orbits an M dwarf. How close is it? Earth takes a year? 365 days.
K2-18b is way, way closer. It whips around its star in just 33 days.
33 days? That's incredibly fast. Faster than Mercury.
Much faster. And because it's so close to its star, it's almost certainly tidally locked.
Tidally locked, right? Like our moon is to Earth, one side always facing the star.
Exactly. One side in perpetual daylight, baking under the star. The other side in permanent nighttime, potentially freezing cold.
Wow, that must create some extreme conditions.
Oh, absolutely. Think about the temperature differences. Huge contrast between the day and night sides. You'd likely have incredibly strong winds trying to circulate that heat around.
So no normal sunrise or sunset, just eternal day or eternal night, depending on where you are?
Pretty much. Maybe twilight zone, a terminator region, in between where the star hangs low.
Yeah.
But yeah, vastly different from Earth's rotation. And huge implications for climate and, well, potential habitats.
Okay, so it's big, massive, orbits quickly, probably tidally locked. What about its density? Is it rocky? Gassy?
That's another fascinating clue. Its density works out to about 2.67 grams per cubic centimeter.
2.67 GC/mO. How does that compare?
Well, Earth, being rocky, is much denser, around 5.5 GC-meter. But an ice giant like Neptune is less dense, about 1.6 GC-meter.
So K2-18b is right in the middle.
Very much smack in the middle, which strongly suggests it's not just a big rock, nor is it just a fluffy gas ball.
Okay, so what does that density imply?
It likely means it has a substantial envelope of lighter materials, probably hydrogen and helium, like a mini gas giant atmosphere. But it must also have a significant core or interior layer that's much denser, perhaps rocky or icy, contributing to that overall mass, a layered structure.
Which leads to its classification then. It's not quite a super-Earth, not quite a Neptune.
Exactly. It falls into this category we call sub-Neptunes. And these are actually incredibly common out there in the galaxy.
Really? Common. But we don't have any here.
Nope. Nothing quite like them in our solar system. They typically range from, say, 1 to 4 times Earth's radius and maybe up to 20 Earth masses. K2-18b fits right in there.
And you mentioned something about a radius valley. Where does K2-18b fit with that?
Ah, the radius valley. Yeah, that's this weird gap in the observed sizes of planets. We see lots of planets smaller than about 1.5 Earth radii and lots bigger than about 2 Earth radii, but fewer in between.
Why is that?
The thinking is that planets in that valley range, the sort of super-Earths, might struggle to hold on to their initial atmospheres. Stellar radiation, internal heat. It might strip those atmospheres away, leaving bare, rocky cores.
Okay.
But K2-18b, at 2.6 Earth radii, is clearly beyond that valley. It's big enough, massive enough, that it managed to hold on to a substantial atmosphere.
And retaining that atmosphere is crucial for, well, for everything else we're going to talk about.
Absolutely crucial.
Yeah.
Especially for habitability.
Which brings us to the kicker. The reason K2-18b got so much attention in the first place, its location.
Its location within the habitable zone of its star.
The Goldilocks zone. Explain that again for us. Why is that so important?
Right, the habitable zone, or Goldilocks zone. It's that region around a star where the temperature is theoretically just right for liquid water to exist on a planet's surface.
Not too hot, not too cold.
Exactly. Not so hot that water boils off into space, not so cold that it's permanently frozen solid. And liquid water, as far as we know from Earth.
It's essential for life.
It's fundamental, the solvent for biochemistry. Facilitates all those crucial reactions. So finding a planet like K2-18b big, with an atmosphere orbiting right in that zone, immediately puts it on the short list of interesting places to look closer.
And that closer look came in 2019, didn't it? That's when K2-18b really made headlines.
It really did. 2019 was the big breakthrough. Scientists announced they had detected water vapor in K2-18b's atmosphere.
Water vapor in the atmosphere?
Yes, published in Nature Astronomy. a major journal, a
Yeah.
team including researchers from University College London. And this wasn't just a maybe, it was a solid detection.
And that was the first time for a planet like this. In the habitable zone.
It was the first time water vapor was confirmed in the atmosphere of an exoplanet orbiting within its star's habitable zone, a huge milestone.
Why was that such a massive deal? We know water is important, but why is finding it in the atmosphere so significant?
Because it hints at a larger water cycle, or at least a significant reservoir of water somewhere on or within the planet. It's not just about surface water. Atmospheric water tells you water is present and active in the planet's system.
Right. It's part of the climate, the chemistry.
Exactly. It raises the possibility of clouds, maybe even rain, though the conditions would be very different from Earth. It makes the planet seem much more dynamic, much more potentially Earth-like in that one specific, crucial way. It really fueled the speculation about habitability.
Okay, so how did they do it? Detecting water vapor 124 light years away seems incredibly difficult, especially back in 2019.
It's a testament to the power of transit spectroscopy, even with older instruments like Hubble.
So this was Hubble, not JWST yet.
Not yet, no, this was Hubble. They used its Wide Field Camera 3, WFC3. Over 3 years, they observed 9 separate transits of K2-18b.
9 times the planet passed in front of its star.
Right, and each time they carefully measured the starlight filtering through the edge of the planet's atmosphere.
Ah, so it's fingerprinted by the atmosphere.
Precisely. Molecules in the atmosphere absorb specific wavelengths, specific colors of light. Water vapor has a very distinct absorption signature in the infrared wavelengths that Hubble's WFC3 could detect.
So they saw that signature, the missing light at water's wavelengths.
They saw that characteristic dip. By analyzing those subtle changes across the 9 transits, they built up enough evidence to confidently say, yes, there's water vapor here. It was a fantastic piece of observational work, really pushing Hubble's capabilities.
Incredible. So Hubble cracked the door open, showed us water was there, but then came the Webb Telescope, JWST, the real powerhouse.
The James Webb Space Telescope, yes, launched in December 2021. And it's a revolution for this kind of science, especially atmospheric characterization.
How so? What makes JWST so much better for this?
Several things. Its sheer size. For one, a much bigger mirror means it collects way more light. But crucially, it's designed to observe primarily in the infrared,
Infrared light, why is that so important?
because that's where many molecules, including water, methane, carbon dioxide, and even potential biosignatures like DMS, have their strongest, most distinct absorption features. Webb can see these fingerprints much more clearly than Hubble could.
Okay, and it avoids other issues too.
Yes, observing in infrared helps minimize problems like stellar contamination interference from the star itself, like star spots. And it reduces the effect of limb darkening, that fuzziness at the star's edge, giving cleaner signals of the planet's atmosphere.
So going from a blurry picture to sharp HD.
Or even 4K color. It's a massive leap in capability.
And naturally, JWST turned its gaze to K2-18b pretty quickly.
Oh yes, it was a prime target. There were 2 key sets of observations in 2023, January and June.
What instruments did it use?
The first used NIRSpec, the near-infrared spectrograph. That gives really high-resolution data, really fine detail in the sort of 2.7 to 5 micron range.
Okay, and the second?
The second used NIRS, the near-infrared imager, and slitless spectrograph. That provides medium-resolution spectroscopy but covers a slightly different, broader range from about 0.85 to 2.85 microns.
So combining these gives a really detailed picture across a wide range of infrared light.
Exactly. A much more complete look at the atmospheric chemistry.
And what did JWST find? Did it just confirm Hubble's water, or was there more?
Well, it definitely confirmed water vapor was present. But the big surprises were the definitive detections of methane, CH4, and carbon dioxide, CO2.
Methane and CO2, okay. Why was that surprising?
Because the amounts were quite significant, especially the methane. And seeing those carbon-bearing molecules so clearly alongside the hydrogen that we assume dominates the atmosphere really starts to paint a picture of a complex, carbon-rich environment. It wasn't just water and hydrogen.
Which gives clues about the planet's interior or maybe even surface interactions.
Potentially, yes. The ratio of these molecules can tell us a lot about the temperature, the pressure, the chemical processes happening deeper down. It immediately made the picture more complicated, more interesting than just a watery world.
Okay, so methane, CO2, water vapor confirmed. But then there was this other signal. Much weaker, much more debated.
Yes. The hint. The potential detection of dimethyl sulfide. DMS.
DMS. This is where things got really exciting and really controversial, right? The potential biosignature.
This absolutely lit up the community
Right.
because DMS here on Earth is overwhelmingly produced by life,
Specifically.
specifically by marine phytoplankton, tiny little organisms in the ocean. It's actually the compound responsible for that characteristic smell of the sea sometimes.
Okay. So if it's almost exclusively made by life on Earth, finding it on K2-18b, the implication is huge.
Exactly. The immediate thought is,
Hmm.
could this be it? Could this be evidence of alien biology churning out this gas?
And the amount they thought they detected wasn't trivial either.
No, the initial reports suggested concentrations maybe 20 times higher than what we find in Earth's atmosphere on average. And DMS is quite fragile. It breaks down relatively quickly in an atmosphere.
So if it's there in large amounts, something must be constantly producing it.
That's the reasoning, yes.
Yeah.
Continuous replenishment seems necessary, which again points towards some kind of active source, maybe biological, maybe geological. We don't know for sure. But it led some astronomers to very cautiously suggest this was one of the most promising hints of a biosignature we'd seen yet.
You can see why that would make headlines. Life chemicals found on distant world.
Precisely. Huge public interest. But science demands skepticism, right?
Always. So what are the counter arguments? Why might this DMS signal not be life? What are the holes in that interpretation?
Well, several big ones. First, there's the issue of other expected chemicals. Scientists like Dr. Shenggen Tsai, Dr. Claire Sousa Silva, and others pointed out, if you have that much DMS being blasted by UV radiation from the star,
Which it would be, orbiting so close.
right, that UV light should break down DMS, and the resulting fragments should react to form other molecules. One molecule you'd strongly expect to see is ethane, C2H6.
Ethane, okay? And did JWST see ethane?
That's the thing. Ethane was not detected, or at least not at the levels expected, if the DMS signal was real and that strong. Its absence, or very weak signal, is a puzzle. It makes you question either the DMS detection itself or maybe our understanding of the atmospheric chemistry on such a weird world.
So it's not just what you see, it's what you don't see that matters too. The whole chemical picture has to make sense.
Exactly. It has to be self-consistent. Then there's the even bigger point. DMS can be produced abiotically, without life.
Oh, how?
Well, we know certain geological processes can produce sulfur compounds, but the real kicker came in 2024.
What happened then?
Scientists analyzing data from the Rosetta mission found DMS on a comet, Comet 67P.
On a comet, a cold, dead comet.
Yep, a cold, lifeless chunk of ice and rock. Finding DMS there definitively proves it's not an exclusive biosignature. It can form through non-biological pathways, maybe involving radiation chemistry on icy surfaces.
Wow, that really puts a damper on the excitement, doesn't it?
It injects a very large dose of caution. It means if we see DMS somewhere, we can't just leap to it must be life.
Yeah.
We have to consider abiotic sources, especially on worlds vastly different from Earth.
Which brings up the whole Earth-centric bias thing. We're applying our understanding of Earth life to a place that's, well, not Earth at all.
It's a massive challenge. K2-18b is a sub-Neptune. High pressures, hydrogen-dominated atmosphere orbiting an M-dwarf. The chemistry happening there, it's almost certainly not going to be just like Earth chemistry.
So maybe DMS is produced there, but through some weird alien chemical process we haven't figured out yet.
Exactly. Researchers emphasize we need lab experiments that simulate these extreme conditions. We need to explore the chemical possibilities in hydrogen-rich environments. As some put it, it's unlikely to be similar to what happens on Earth. We might be missing entire abiotic pathways because we're stuck in our Earth-based thinking.
Okay, so chemical inconsistencies, abiotic production possibilities. Were there also issues with the JWST data itself? Different analyses, maybe?
Yes, that adds another layer of complexity. An independent analysis came out later, combining data from 3 JWST instruments, NISPEC, NIRISE, and MIRI, the mid-infrared instrument.
MIRI sees even longer infrared wavelengths.
Right. And this combined analysis found, well, very little evidence supporting the DMS detection.
Really? So conflicting results from the same telescope?
Kind of. They found that the supposed DMS feature seen in the MIRI data didn't quite match up with expectations from the shorter wavelength data from NRSPEC and ERS. It seemed too strong in MIRI wavelengths. And to make that MIRI feature fit, they needed to assume atmospheric conditions like a much higher temperature or a more puffed up atmosphere that just weren't consistent with what the other instruments were seeing.
So the different pieces of data weren't telling the same story if you included DMS?
Pretty much. Their conclusion was quite sobering. They calculated we'd need to observe something like 25 more transits with the RI just to be statistically confident whether the signal is real DMS or just, well, noise, a flat line.
25 more transits. That's a lot of telescope time.
A huge amount. It really underscores how tentative that initial DMS hint was.
So summing up the DMS saga, exciting hint, potential game changer, but very much unconfirmed, needs a lot more work.
That's the perfect summary. It's a big teaser, as some called it. Highly intriguing, pushes the science forward, but tentative and requires further validation are the key phrases. It's science working as it should. Claim, scrutiny, demand for more evidence.
This uncertainty about the atmosphere, the DMS, even the amount of water, it leads us to this fundamental question about K2-18b's identity. Is it this potentially habitable Hycean world, or is it something else entirely? The interpretations seem to diverge quite dramatically.
They really do. Even with the amazing JWST data, scientists are interpreting it in different ways, painting very different pictures of the planet.
What are the main competing ideas?
Broadly, you have the Hycean world camp thinking it's a planet with a global liquid water ocean under a hydrogen-rich atmosphere. Then you have others leaning towards it being more like a gas-rich mini-Neptune, maybe without a distinct surface ocean at all, just a gradual transition from gas to denser fluid.
If a fuzzy boundary instead of a clear ocean surface.
Possibly. It highlights how little we understand about these sub-Neptunes, these planets that don't exist in our solar system. We're still trying to figure out their basic structures.
And the planet's insides, its internal structure, are key to this too, right? That density clue doesn't tell the whole story.
No, it gives us the average, but not the layers. Remember, the density is about 2.67 GC No, that definitely points to a big hydrogen envelope. But what's underneath?
Right.
Is it a massive rocky core, maybe like a super Earth core, buried deep beneath thousands of kilometers of hydrogen? Or is it more like Neptune's interior, with thick layers of exotic ices, water ice, ammonia ice, methane ice under high pressure, again, topped by hydrogen?
Or could it be mostly water, a true water world?
A pure water planet with a thin atmosphere seems less likely given its overall size and mass. It needs that significant lighter envelope to match the observed radius and density. But a very, very deep water layer, perhaps transitioning it to high-pressure ice phases under the hydrogen atmosphere, that's certainly a possibility being considered.
And the fact it orbits an M dwarf plays into its atmosphere's evolution too, doesn't it?
Yeah.
These atmospheres aren't static.
Not at all, especially around M dwarfs. These stars can be very active, particularly when young, blasting their planets with flares and radiation.
Which can strip away atmospheres.
It can. Over billions of years, photoevaporation of the star's energy boiling off the atmosphere can significantly change a planet's atmospheric composition. It might start with a thick hydrogen-helium atmosphere from formation.
A primary atmosphere.
Right, a primary atmosphere. But stellar activity might strip away much of the hydrogen, maybe allowing heavier gases released from the interior like water, CO2, nitrogen, through volcanism or outgassing to become more dominant over time.
Leading to a secondary atmosphere like Earth's.
Or, perhaps more likely for K2-18b, something in between, a hybrid atmosphere.
Hybrid, meaning
It might have retained a good chunk of its original primary hydrogen atmosphere, but it's also been significantly enriched with heavier molecules outgassed from below or maybe delivered by impacts. That mix of hydrogen, methane, CO2 we see could be the signature of this hybrid nature. K2-18b's current state might just be one chapter in a long, dynamic story.
Okay, let's circle back to that Hycean world idea. It's a really evocative concept. What exactly defines a Hycean world?
It's a relatively new proposed class of exoplanets. The name combines hydrogen and ocean, so Hycean.
Hydrogen ocean worlds.
Exactly. The hypothesis is these are planets characterized by a vast, global, liquid water ocean, potentially hundreds or thousands of kilometers deep. But unlike Earth, this ocean isn't under a nitrogen-oxygen atmosphere. It's under a thick, crushing, hydrogen-rich atmosphere.
Wow, so imagine Earth's oceans, but way deeper, covering the whole planet, and with a Jupiter-like atmosphere on top.
Kinda, yeah. But perhaps warmer than Jupiter? And K2-18b, with its size, its location in the habitable zone, and its hydrogen-rich atmosphere with water vapor. It's considered a prime candidate for this type of world. It really stretches our definition of habitable.
If it is Hycean, what does that mean for life? It sounds incredibly alien, but could life exist there?
That's the multi-billion-dollar question. If it's Hycean, the conditions could be very strange, but maybe not impossible for life. The surface temperature of the ocean under that thick hydrogen blanket could potentially be warm enough for liquid water.
Even though it's far from its dim star, the hydrogen acts like a greenhouse gas.
A very effective one, yes. And warmer temperatures could, theoretically, lead to faster chemical reactions, maybe higher rates of evolution, potentially stronger biosignatures if life exists. Maybe that DMS signal, if real, fits with the productive Hycean ocean.
But life there would have to be tough, right? Extremophiles.
Almost certainly. Life would need to cope with immense pressure at the bottom of that deep ocean, maybe different radiation levels filtering through the atmosphere, and the specific chemistry of a hydrogen-dominated environment.
And photosynthesis would be different too. M dwarfs give off different light.
Right, they emit less visible light and more infrared light than our sun. So any photosynthetic life might have evolved to use near-infrared wavelengths, maybe using pigments completely different from chlorophyll. Think purple or black plants, perhaps?
Yeah.
It's fascinating speculation.
Okay, so that's the optimistic Hycean picture. But there's this other, much less welcoming possibility you mentioned earlier, the supercritical water ocean.
Yes, this is an alternative interpretation of the JWST data, particularly the chemical ratios, that paints a very different, much hotter picture.
A hydrothermal world, basically.
Essentially, yes, a planet-wide hydrothermal system where the ocean isn't really liquid water as we normally think of it.
Because it's supercritical. Remind us what that means again. It's not liquid, not gas.
It's a state. Water reaches above its critical point, which is about 374 degrees Celsius and 220 times Earth's atmospheric pressure. Above that point, the distinction between liquid and gas disappears. Water becomes a single, dense, hot fluid phase.
So on K2-18b, if this model is right, there's no ocean surface.
Probably not a distinct one. You'd have this deep layer of hot, dense, supercritical water fluid that just gradually and seamlessly merges into the hydrogen atmosphere above it. No boundary, just a very strained, very hot transition.
And what's the evidence pointing towards this scenario? You mentioned chemical ratios.
Yes, the observed ratio of methane, CH4, to carbon dioxide, CO2 in the atmosphere. To get the observed ratio through chemical equilibrium reactions, models suggest the interacting ocean surface needs to be hot. Really hot.
How hot?
The minimum temperature inferred from the CH4-CO2 ratio is around 710 Kelvin, that's over 400 Celsius, well into this supercritical regime for water.
Wow.
And another ratio involving carbon monoxide, CO, although less certain, allows for even higher temperatures, maybe up to a 1070 Kelvin or 800 Celsius. These temperatures fit much better with a hot supercritical fluid interacting with rock below and atmosphere above, rather than a cooler liquid ocean.
And the implication for life is pretty bleak.
For life as we know it, yes, completely bleak. Temperatures above 400, 500 Celsius. That's far beyond the known limits for even the toughest extremophile microbes on Earth. It would essentially sterilize the planet by our standards.
So the same planet, the same data, could be interpreted as either a potential haven for weird life or a hellish, supercritical pressure cooker.
That's the crux of the current debate. It highlights just how much interpretation goes into analyzing this distant data and how our models shape what we conclude. It's a stark reminder that habitable zone doesn't automatically mean habitable conditions.
How on earth do scientists tell these scenarios apart then? It seems like we need more specific clues.
Absolutely. And the key lies in getting better measurements of other molecules, particularly carbon monoxide, CO, and ammonia, NH3.
Why those two?
Because the different models, the cooler Hycean world, the hot supercritical world, or just a gas-rich mini Neptune with no real surface interaction, predict different amounts of CO and NH3 in the atmosphere.
Ah, they act like diagnostic tests.
Exactly. For instance, a very hot supercritical ocean interacting with rock might produce more CO. The amount of ammonia might tell us about mixing between different layers. Nailing down the abundances of CO and NH3 is probably the next critical step for JWST observations, to try and break the deadlock between these competing models and really understand K2-18b's true nature.
It's just incredible how we can even attempt this, peering into atmospheres light years away. Let's take a step back and talk about the toolkit. How do we find these planets in the first place?
Yeah, the discovery methods themselves are amazing feats of engineering and observation. It's a relatively young field, really kicked off in the 90s.
Before the 90s, it was all just theory.
Mostly science fiction and theory, yeah. The first confirmed exoplanets weren't even around a normal star. In 1992, Alexander Voltsan and Dale Frail found planets orbiting a pulsar.
A pulsar, the remnant of a dead star. How?
By measuring tiny variations in the timing of the pulsar's radio pulses, it was completely unexpected. How could planets survive a supernova or form afterwards? Still debated.
Wow. But the big one, the one that really opened the floodgates.
That was 1995. Michel Mayor and Didier Queloz discovered 51 Pegasi b, the first planet found orbiting a sun-like star. That discovery won them the Nobel Prize, and rightly so. It proved planets around normal stars were real and detectable.
And since then, boom, over 5,600. What are the main ways we find them? You mentioned the transit method for K2-18b.
Yes, the transit method is the king right now, responsible for the majority of discoveries, thanks largely to Kepler and now TESS. It's conceptually simple. You watch a star very carefully, looking for a tiny periodic dip in its brightness.
Caused by a planet passing in front, blocking a little bit of light.
Exactly, like a tiny eclipse. The amount of dimming tells you the planet's size relative to the star, and the time between dips tells you its orbital period.
Okay, that's number one. What's the other major player?
The radial velocity method, or the Doppler wobble method. This was how 51 Pegasi b was found. It doesn't look for dimming light, it looks for a star moving.
The star moves because the planet is pulling on it.
Precisely. As a planet orbits, its gravity tugs the star back and forth ever so slightly around their common center of mass. This tiny wobble causes a Doppler shift in the star's light.
Like the sound of an ambulance siren changing pitch.
Exactly like that. When the star wobbles towards us, its light shifts slightly towards the blue end of the spectrum. When it wobbles away, it shifts towards the red. By measuring these tiny periodic shifts, we can infer the presence of a planet and estimate its minimal mass and orbit.
So transit tells us size, radial velocity tells us mass. Together they give density, right?
Yes, combining both methods for the same planet is incredibly powerful. That's how we get density measurements,
Right.
like the one for K2-18b, which tells us so much about its likely composition.
Are there other ways to find planets too? Less common ones.
Yes, several others, each useful in different situations. There's gravitational microlensing.
Microlensing, using gravity as a lens.
Kind of. If a star with a planet happens to pass almost directly between us and a more distant background star, the gravity of the foreground star and its planet can bend and magnify the light from the background star. The planet adds its own little extra blip to the magnification event. It's rare, but good for finding planets far from their stars, even free-floating planets.
Wow, okay, what else?
Direct imaging. This is the holy grail for some actually taking a picture of the planet itself.
But that's super hard, right? Planets are faint, stars are bright.
Incredibly hard. It requires sophisticated techniques to block out the overwhelming starlight, usually using coronagraphs and adaptive optics. It works best for large, young, hot planets that are very far from their stars. We have some amazing images, but relatively few planets found this way so far.
Still amazing that we can do it at all. Any others?
A couple more main ones: astrometry, which is related to radial velocity, but instead of measuring the Doppler shift, it tries to precisely measure the star's tiny side-to-side wobble against the background stars over many years. Very challenging. And minor methods like timing variations, like the pulsar method, but also used for planets orbiting binary stars, and orbital brightness modulation, detecting the faint reflected light from the planet itself as it orbits.
So a whole arsenal of techniques. But transit and radial velocity are the workhorses that found most of the thousands we know.
Definitely. If you look at the discovery curves over time, you see transit detections just shoot up once Kepler launched. It was revolutionary.
Okay, so you find a planet. Then comes the really exciting part, figuring out its atmosphere. Back to transit spectroscopy. How does that work again, fundamentally?
So you found a planet that transits. Now, you observe that transit not just in total brightness, but broken down by wavelength using a spectrograph, as the starlight passes through the planet's atmospheric limb.
The edge, the sliver of atmosphere we see silhouetted.
Right. The gases in that atmosphere absorb specific wavelengths of the starlight. So when you look at the star spectrum during the transit, certain colors will be dimmer than others, corresponding to the molecules present in the atmosphere.
Creating those chemical fingerprints?
Exactly. It's like holding a filter up to the starlight, where the filter's properties are determined by the atmospheric composition. The first big success was detecting sodium in the atmosphere of the hot Jupiter HD 2-9458b back in 2002, a landmark moment.
What's actually happening at the molecular level during this absorption?
It's quantum mechanics in action. Photons of light carry specific amounts of energy. Molecules can only exist in specific energy states, electronic states, vibrational states, rotational states. If an incoming photon has exactly the right amount of energy to bump a molecule up from a lower state to a higher allowed state, the photon gets absorbed.
So the molecule eats that specific color of light.
Precisely. Electronic transitions, electrons jumping orbits, usually absorb higher energy UV or visible light. Vibrational transitions, atoms within the molecule wiggling faster, and rotational transitions, the whole molecule spinning faster, absorb lower energy infrared light. That's why infrared is so good for seeing molecular signatures.
Okay, absorption makes sense, but you mentioned scattering too. How does that affect things?
Scattering just redirects light rather than absorbing it.
Hmm.
Tiny gas molecules cause Rayleigh scattering, which preferentially scatters shorter wavelengths, blue light, more strongly. That's why our sky is blue. Larger particles, like haze or cloud droplets, cause Mie scattering, which affects different wavelengths differently depending on particle size. Both types of scattering can affect the overall shape of the spectrum we observe, sometimes making it harder to see the distinct absorption features or telling us about clouds and hazes.
And there was that other weird one, collision-induced absorption, CIA.
Ah, yes, CIA. It's important for molecules that don't normally absorb infrared light well on their own because they're symmetric, like hydrogen, H2, nitrogen, N2, or even methane, CH4 to some extent. They don't have a permanent separation of charge, a dipole moment.
Okay.
But when these molecules collide forcefully in a dense atmosphere, the collision itself can temporarily distort their electron clouds, creating a fleeting dipole moment. And during that brief instant, they can absorb infrared photons. In dense hydrogen-rich atmospheres like K2-18b's likely has, CIA by hydrogen colliding with itself or other molecules can be a significant source of opacity, influencing the overall spectrum.
Wow, okay. So many subtle effects to account for. And you mentioned limb darkening before, how observing in infrared helps with that.
Right, limb darkening. Stars look brighter in the center than at the edge. This happens because at the edge, our line of sight passes through only the shallower, cooler, less bright upper layers of the star's atmosphere.
Okay.
This affects the shape of the transit light curve, making it less like a sharp drop and more rounded.
Mm.
This rounding can make it harder to precisely measure the timing and depth, which affects atmospheric measurements. But this limb darkening effect is much less pronounced at longer infrared wavelengths.
So the star looks more uniformly bright in infrared.
Pretty much, yes, which means the transit shape is cleaner, sharper, more like a U than a V. This gives a much better baseline for measuring the tiny atmospheric absorption signals superimposed on top of it. Another huge advantage for JWST.
Makes sense. But then there are clouds, the ultimate party crashers for atmospheric scientists.
They can be, yes. Clouds or hazes high up in an exoplanet's atmosphere can completely block the starlight from reaching the deeper layers, where we expect to find interesting molecules.
So you just see the clouds, not what's underneath.
Often, yes. Clouds tend to absorb or scatter light fairly uniformly across a wide range of wavelengths, creating a flat or muted spectrum. Instead of seeing sharp absorption peaks from water or methane, you just see this gray, featureless slope caused by the clouds. It makes it incredibly difficult, sometimes impossible, to figure out the composition below. They are a major headache in interpreting spectra.
So with all these complex factors, absorption, scattering, CIA, limb darkening, clouds, how do scientists actually piece together what an atmosphere is made of? It sounds like untangling a huge knot.
It is. And that's where sophisticated computer modeling and statistical techniques known as atmospheric retrieval come in.
Retrieval, like retrieving the information from the tangled data.
Exactly. Frameworks like TORAX-3, which you mentioned, are designed for this. They essentially work backwards from the observed spectrum. They simulate thousands, even millions, of possible atmospheres. They vary all the parameters, the abundance of different molecules, water, methane, CO2, etc., the temperature profile at different altitudes, the properties of clouds, how high, how thick particle size, and so on.
Okay, millions of what-if atmospheres.
Right. For each simulated atmosphere, the model calculates what its transit spectrum should look like, including all those effects like absorption, scattering, and clouds. Then it compares that simulated spectrum to the actual observed data from Hubble, or JWST.
And tries to find the best match.
Precisely. Using complex statistical methods, often Bayesian inference algorithms like multinest, it figures out which combination of atmospheric parameters provides the best fit to the real data. It doesn't just give one answer. It gives a probability distribution for each parameter, like water abundance is most likely between X and Y, or clouds are probably present above Z altitude. It's a computationally intensive process of exploring possibilities and finding the most plausible atmospheric recipe.
Incredible. It's like solving a massive inverse puzzle. Now, K2-18b orbits an M-dwarf. We touched on this, but why are M-dwarfs so central to exoplanet research?
Several key reasons. First, sheer numbers. M-dwarfs are the most common type of star in the Milky Way, making up maybe 70% or even 75% of all stars.
So statistically, most planets are probably orbiting M-dwarfs.
Exactly. If planets are common and M-dwarfs are common, then planets around M-dwarfs must be super common. If life exists elsewhere, chances are good it might be around an M-dwarf.
And they have observational advantages too, right? You mentioned that earlier.
Yes. Because M dwarfs are smaller and dimmer than the sun, their habitable zones are much closer in.
Which means planets orbit faster, more transits.
Yep, more frequent transits mean we can gather data faster, and the transits themselves are deeper, more pronounced. A planet blocking a small M dwarf blocks a larger fraction of its light compared to the same planet blocking a big sun-like star.
Easier to detect the dip.
Much easier. And crucially, the atmospheric signal during transit is also proportionally larger. The starlight passes through the same amount of atmosphere, but relative to the smaller star, that atmosphere makes a bigger impact on the light we see. So atmospheric characterization is generally easier around M dwarfs.
But it's not all good news, right? The double-edged sword.
Right. M dwarfs, especially younger ones, can be very magnetically active. They often have powerful stellar flares and emit strong X-ray and UV radiation.
Which could be bad for life, or even for atmospheres.
It could be. Constant bombardment by high-energy radiation could potentially strip away planetary atmospheres over time, especially the lighter gases like hydrogen. Or it could create hostile surface conditions, bathing the planet in harmful radiation. Tidal locking, which is common for habitable zone planets around M dwarfs, also creates extreme temperature contrasts. So, while they're great targets for finding and studying planets, the actual habitability of M dwarf planets is still a really active area of research and debate. Being in the zone isn't enough.
Okay, so we've covered the history, the planet, the methods, bringing it all back to K2-18b. Despite JWST's power, we're still left with this uncertainty, these competing models. What are the absolute limits right now?
The fundamental limit is that, even with JWST, we cannot yet definitively distinguish between those main scenarios: the potentially habitable Hycean world, the hotter supercritical ocean world, or just a gassy mini-Neptune envelope without a clear surface interaction.
The data fits multiple stories.
The current data allows for multiple interpretations. It leans towards maybe a complex hybrid atmosphere, but the exact nature, the conditions at depth, remain ambiguous. We have to remember we're interpreting incredibly faint signals from light that traveled 124 years to reach us. It's amazing what we can infer, but precision is still limited.
It's easy to forget that. We see these detailed atmospheric graphs, but they're built on minuscule variations in light. Little data to go on, relatively speaking.
Exactly. And the same goes for the planet's deep interior. Is it rock? Is it exotic ices? Is it mostly water? The mass and radius alone don't give a unique answer.
Yeah.
Different internal structures can produce the same overall density. That internal structure is crucial for understanding long-term habitability, things like geological activity, magnetic field generation. But it's even harder to probe than the atmosphere.
So where do we go from here? What's the path forward for understanding K2-18b and planets like it?
More data, better data. Continued JWST observations are top of the list. We need more transits, maybe using different instrument modes, aiming for higher precision and broader wavelength coverage.
To nail down those key molecules like DMS, CO, NH3.
Precisely. Confirming or refuting the DMS signal is obviously a huge priority. And getting really solid measurements of CO and NH3 abundances is probably the best bet for distinguishing between the Hycean and supercritical ocean models. Those molecules are the diagnostic keys we need.
And it's not just about observing, but also improving the models, right?
Absolutely. New modeling and exploration are crucial. Scientists are developing better global circulation models, GCMs, specifically for these weird sub-Neptune atmospheres, trying to understand heat transport on tidally locked worlds with hydrogen atmospheres. How do winds move heat from the day side to the night side? How do clouds form and behave? Better models help us interpret the observations more accurately.
And exploring other possibilities too, like exomoons.
Yeah, that's another fascinating area. Could a large moon orbiting K2-18b be habitable, even if the planet itself isn't? Are such moons stable? These theoretical studies add another dimension to the search.
This whole deep dive really hammers home how our idea of a habitable planet is constantly expanding, constantly being challenged. It's not just about finding Earth 2.0 anymore.
Not at all. K2-18b is a perfect example. It forces us to consider these radically different planetary architectures, Hycean worlds, supercritical worlds, and ask, could life exist there, even if it's utterly unlike Earth life? It pushes us beyond our Earth-centric biases and opens our minds to the sheer diversity of possibilities the universe might hold.
It's been an incredible journey through the science of K2-18b. It really captures the whole process, doesn't it? The initial excitement, the follow-up discoveries, the challenging data, the competing theories. It's science in action.
It really is. A story of iterative discovery. Each new observation refines our understanding, sometimes confirms things, sometimes throws a wrench in the works, and forces us to rethink everything. It's a testament to the power of observation and the importance of rigorous scientific debate.
So let's leave our listeners with a final thought to chew on. What if K2-18b, this poster child for potentially habitable exoplanet, this world that sparked so much excitement, what if it actually turns out to be the supercritical version? Too hot for life as we know it.
And what if that tantalizing hint of DMS, the potential biosignature, turns out to be nothing more than an abiotic chemical quirk, a cosmic red herring?
How does grappling with that possibility change how we search for life? How does the scientific wrestling match force us to question our assumptions about where life could be and what it might look like?
It forces humility, I think. It shows us the search isn't just about finding another Earth. It's about truly understanding the vast, complex, and often surprising range of worlds that exist. K2-18b, whatever its true nature, is teaching us invaluable lessons about planetary science and the intricate conditions that might or might not allow life to arise and thrive in the cosmos. It's a reminder that the universe is likely far stranger and more diverse than we can yet imagine.
A humbling and wondrous thought indeed. Thank you for guiding us through that incredible complexity. And thank you for joining us on the deep dive. We'll be back next time to explore another fascinating topic.